Welcome. Today we're going to be talking about reaction mechanisms, and our goal today is to learn how the rate of a reaction is related to how the reaction itself actually happens. The way that we're going to describe how a reaction happens is called the reaction mechanism. A reaction mechanism is a stepwise description of how a chemical reaction occurs. Every reaction can be understood as a series of processes, that is, a series of collisions, bond breaking, bond forming, bond rearranging, and anything in between, and each process is called an elementary step. So we can basically break a reaction down to a series of steps to understand exactly how that reaction takes place. Now, to better understand what a reaction mechanism is and how it's related to the kinetics of a particular chemical reaction, we're going to look at the following chemical reaction. This right here is a nucleophilic substitution reaction, which is a fairly simple reaction in which one thing is being substituted for another. So right here we have chloromethane that has a chlorine bonded to a carbon, and in this reaction, a bromide is going to come in and replace the chlorine so that you're left with bromomethane and a chloride. So you're going to be breaking this bond between chlorine and carbon, and you're going to form a new bond between this bromine here and carbon. So we want to know how this reaction takes place, and we're going to use kinetics in order to figure that out. All right, so we could basically look at this reaction in a couple different ways. First of all, it could happen in two elementary steps. It could happen in one step where you're breaking this carbon-chlorine bond right here, and you're going to form a positively charged carbon right here called a carbocation and a free chloride. And in the second step, you're going to take this intermediate right here, this positively charged carbon, and you're going to form a bond between it and bromine. And so in these two elementary steps, the first step you're breaking a bond, and the second step you're forming a bond, and overall you're going to end up with this product right here. All right. Now, a couple things to note in this mechanism. The arrows that you see in this mechanism, for example, this arrow right here and this arrow right here, each of those arrows indicates the direction the electrons go. So in this case, the two electrons from this bond are all going to be going to this chlorine right here. And so the carbon ends up that it is now no longer an octet. It has only 6 valence electrons around it. And this chlorine here has both of the electrons from the bond, and it now has 8 valence electrons around it. In this case down here, a lone pair from the bromide is going to be forming a new bond with carbon here. And so you can see the electrons from the bromine are going in this direction to form a new bond with carbon. It's important to note that this right here, this species here, and this species here, which is the same thing, is an intermediate. An intermediate is a species that is produced in one step and consumed in another step. So it's not a reactant and it's not a product. It's just a temporary species that exists and is observable, could possibly be isolated, although not necessarily, is generally a fairly reactive species, but is formed in one step and is consumed in another step, so you don't have any of it left over by the time the reaction is done. Alternatively, the reaction could happen in just one step. So we can imagine that this bromine can come in here to form a bond with carbon at the same time as this bond with chlorine is breaking. And so this can be pictured through the following transition state. So you have a partial bond here between carbon and bromine, and a partial bond here between carbon and chlorine. And that's the process in which this whole thing could happen in one single step. This right here, a transition state, is not an intermediate. A transition state is a completely unstable species. It is going to be the highest energy species in the progress of a reaction. Unlike an intermediate, which can be observed and can possibly be isolated, an intermediate is metastable, that is stable temporarily. A transition state is something that's completely unstable and is just in the process of that one step, but is not formed in any step of the reaction. Now, the rate law of this particular reaction will tell us which of these two different possible mechanisms is actually the mechanism of the reaction. Now, we can't exactly prove one mechanism, but we can at least disprove one mechanism, and we can say which mechanism is most likely to occur. So let's go ahead and check this out. Let's get in a little bit more detail here. So this right here is a reaction profile for one of those different possible mechanisms. And looking at that, let's go ahead and label a few things. Like any reaction profile, you've got the reactants over here, products over here. This curve here that goes up, you have a hump here, you have another hump here. That is all got to do with the kinetics. It's got to do with how the reaction takes place, and it's got to do with the energy involved. Now, as you're looking at this reaction, I want you to pause and think, is this an exothermic reaction or an endothermic reaction? And how do you know? Well, if you look at this, you should realize that this is an exothermic reaction, and we can tell because the reactants have a higher potential energy than the products. And so in this reaction, in this process, the chemicals are losing energy. They're going down in energy, and that energy is going to be given off in the form of heat or some other form of energy. Remember that the distance between the reactant's energy and the product's energy, which is right down here, is the enthalpy of the reaction. And so the enthalpy of the reaction here is negative, slightly negative, so it's slightly exothermic. And you can get the value, if we had actual energy values over here, you could get the value of delta H for the reaction. How about the activation energy? The activation energy is going to be the distance from the reactants up to the very top of this peak right here. That's the activation energy for the reaction, and you can see that it's fairly large in this case. We're going to abbreviate activation energy as E sub A. In addition, I'd like you to pause this video and think about this question right here. How many steps does this particular reaction have? If you said 2 steps, you're correct. Because the reaction profile has 2 humps in it seen here and here, you can tell that this reaction has 2 different steps to it. So here's the first step, and here's the second step. However many humps your reaction profile has is the number of steps that the reaction has. Now let's go ahead and label a couple other things on this reaction profile right here. First of all, let's think about this. What is this local minimum right here? Well, that's going to be an intermediate for the reaction. So here's your step 1, and after step 1, you have an intermediate formed, one or more intermediates. And then here's your second step. And so you can see that this local minimum right here corresponds to an intermediate. Now, what about the tops of each of these humps? This top here is a transition state, and this top right here is a transition state. Transition states always occur at the top of these different humps. We can even go ahead and label and see what each of those different things is. And so in this case here, we have our reactants. And if this is the 2-step process, this should be our intermediate. And our transition states, it's hard to say exactly what they're going to look like, but in this first step, we are breaking a bond between carbon and chlorine. So our transition state should look like a partial bond between carbon and chlorine here. And this next transition state here should look like a partial bond between carbon and bromine as you're going to make your product right here. But you can see clearly that the local minimum or the bottom of this hump right here is going to correspond to your intermediates of the chemical reaction. All right, let's continue on and see how kinetics is going to enable us to tell which of these 2 different possible reaction mechanisms is most likely. All right, the rate law of any elementary step is equal to a constant times the molarity or partial pressure of every reactant involved in that step. So for example, if this is the way an elementary step looks, your rate law for that particular elementary step is going to be the rate equals a constant here times the molarity of A times the molarity of B. Because, well, what is this actually saying? This is saying that in this step, A is going to collide with B and they're going to do something. And in that something that they're going to do, they're going to form C and D. And we can look at this for a bunch of different possible elementary steps. No, not looking into the details of what the atoms are actually doing, but in this process, so this right here is called a unimolecular process. So if just one reactant, A here, goes and turns into products or turns into some kind of intermediates or turns into something else in an elementary step, the rate law for that particular elementary step is simply the rate equals a constant times the molarity of A. If you have a bimolecular step, now, each of these is 2 different possible bimolecular steps. So, for example, you have one species, one chemical bumps into and reacts with itself to form different products. The rate law for that is simply going to be a constant times A squared. And the same thing is going to be true if you have a bimolecular process for one chemical bumping into a different chemical. In that process, you have two things bumping into each other and reacting. And the rate law in that case is going to be a constant here times A times B. Now, right down here, these three processes right here are termolecular processes. That is, they are processes in which three different atoms or molecules collide all at the same time. All right. This is not a case where A bumps into A, waits for a second, and they get stuck together, and then another A bumps into it. No, a termolecular process is a process in which all three species bump into each other at exactly the same time. Because if you can imagine A bumping into A and then getting stuck together and then subsequently bumping into another A, that would be two different steps. Right here, this is three A particles all bumping into each other at the same exact time. So in that case, the rate is going to be equal to a constant times the molarity of A all cubed. In general, termolecular steps are going to be so rare, it's going to be very rare that you got three particles all bumping into each other at exactly the same time. So because they're so rare, we're going to consider any mechanism with a termolecular step as virtually impossible. Now, it's not completely impossible, but it's probably going to be a pretty bad mechanism. Simply because bimolecular collisions occur so much more frequently, that mechanism that includes bimolecular rather than termolecular processes is going to be much more likely. And so we can pretty much ignore all three of these different possible termolecular steps. Usually, one step in a chemical reaction is significantly slower than the other steps. The slowest step of a reaction is called the rate determining step. And that is because the rate of a reaction equals the rate of the slowest step. All right, that's very important. It's called the rate determining step. The slowest step is always called the rate determining step because the rate of the reaction is equal to the rate of the slow step. So to help us visualize that, let's think about three different funnels. One of those three different funnels is particularly small and narrow, so the water is going to go through that funnel fairly slowly. So no matter where we place that narrow funnel, whether we make it the first step or the second step or the third step in this process of pouring water out, that narrow funnel is going to be the slow funnel, and it's going to determine how fast the water goes through. All right. And so in all three cases, regardless of where we place that funnel, the water is going to go through them the same exact speed. All right. Now let's go ahead and go back to that nucleophilic substitution reaction, and let's think about the two-step process. Go ahead and pause the video and think about which step do you think should be the slow step in this process. If you said that the first step is a slow step and the second step is the fast step, you're correct. Why is that? Well, think about it. In general, breaking bonds is a lot more difficult to do than forming new bonds. So in this first step, we're breaking this bond between carbon and chlorine, and we're forming a fairly unstable non-octet positively charged carbon right here. In the second step, we are forming a bond, and we're now taking this unstable species and making something much more stable. And so in general, bond breaking is going to be much slower than bond forming. Now let's go ahead and look at this a little bit more in detail and think about, well, all right, now we know which step is the slow step and which step is the fast step. Well, how do we go about determining the overall rate law of the reaction? Well, let's look at each of these elementary steps. This first step right here, the slow step, you've got this species here that's not bumping into anything else, is just reacting all by itself. And in that process, you're breaking a bond. So the rate law for the first step should simply be a constant times the concentration of this species right here. Because it's a unimolecular elementary step, the rate law is just a first order step. Now, what about the second step right here? The second step, the fast step, involves forming a bond between this carbon and this bromine, and so you actually have two different species that must collide in order for this process to take place. And so because you have a bimolecular elementary step, those two things are bumping into each other, the rate law is going to look like this. The rate equals another rate constant times the concentration of this times the concentration of this. Now that we have the rate law of each of those elementary steps, let's think about, well, what is the overall rate law for this chemical reaction? Well, remember that this right here is the slow step, which means that that first step, the slow step, is the rate determining step, which means that the rate law for the overall reaction is equal to the rate law of that elementary step. So we can now say for this overall chemical reaction, the rate law is simply a constant times the molarity of chloromethane, and that's it. The rate law should not include the concentration of the bromide. Now let's go ahead and compare this to the alternative mechanism. Remember, the alternative mechanism is bond breaking and bond forming occurring at the same time, all in one elementary step. So if this mechanism occurs in one single elementary step, what do you think the rate law for this mechanism is going to be? Well, because this is a bimolecular process, you got two things bumping into each other in that one elementary step. The rate law is going to be this. It's going to be a rate constant times the concentration of this species times the concentration of this species. And so you have both of those appear in the rate law. And this, therefore, is overall second order because it's first order in both of the chemical reactants. All right, now we can go ahead and summarize what we've figured out from these two reaction mechanisms and compare them to actual kinetics data. So we have two possibilities. We have a two-step mechanism, and in the two-step mechanism, the rate is simply going to be a rate constant times the concentration of this reactant. And if you have a one-step mechanism, the rate is going to be a rate constant times the concentration of both of those different reactants. And so we have two different rate laws, and because there are two different rate laws, we can definitively tell which one of these mechanisms is most likely. Now, before I tell you which one is correct, I do want to emphasize that the rate law of a reaction can only be determined experimentally. The experimentally determined rate law tells us about how a reaction works. It turns out that experimentally, this reaction is first order in both of the reactants, in both chloromethane and bromide. And so therefore, the two-step mechanism is not supported by the kinetics. In fact, it's most likely going to be a one-step mechanism for this chemical reaction. Now, we went to all that trouble looking at a one-step mechanism and a two-step mechanisms. It turns out that not all nucleophilic substitution reactions work exactly the same way. So if we compare this reaction that we just looked at, remember this reaction is second order overall because it is a one-step process. But sometimes there's other species, for example, this compound right here, in a fairly similar reaction where we're replacing this chlorine with a bromine. This actually has a completely different rate law, and the rate law for this reaction is actually only first order overall and doesn't depend on the concentration of the bromide. And so what does that tell you about that particular process? It tells you that, well, this reaction occurs through a most likely a one-step reaction mechanism. The second reaction right here most likely occurs through a two-step process where you're first breaking that carbon-chlorine bond and subsequently forming a different carbon-bromine bond. In addition to the rate law, there's a bunch of other experiments that we can do to help us understand how these different chemical reactions take place. But for right now, let's just go ahead and focus on kinetics and reaction mechanisms. We're going to go ahead and end there. Stay curious. See you next time.